Welcome to Lecture 12 in Mathematical Foundations of Robotics. In this lecture we want to discuss an important class of sequences, monotonic sequences. Let's start with a definition. Let an be a sequence of real numbers. We say that an is strictly increasing if an plus 1 is larger than an for every natural number. We say that an is weakly increasing if an plus 1 is larger than or equal to an for every natural number. The same way we define an as strictly decreasing if an plus 1 is strictly less than an for every natural number n, and it is weakly decreasing if an plus 1 is less than or equal to an for every natural number n. So in all these cases, all of this, they can be considered as monotonic sequences. It is easy to observe, just like we did for the real functions, that clearly strictly increasing implies weakly increasing, and similarly strictly decreasing implies weakly decreasing. Of course, the opposite is never true. An alternative definition for monotonic sequences is the following. We could say that an is strictly increasing if given m larger than n implies that am is larger than an, and it is weakly increasing if m larger than n implies that am is larger than or equal to an. Then we have that an is strictly decreasing if m larger than n implies that am is strictly less than an, and finally that an is weakly decreasing if having m larger than n implies that am is less than or equal of an. Okay, so another important concept we want to define now is the what are the bounds of a sequence. So we have another definition in place now. We say that a sequence an is upper bounded, and we simply write UB if there exists at least one real number m such that every element of the sequence an will be less than or equal to m for every natural number n. We say that the sequence is lower bounded LB if there exists at least one real number m such that an is larger than or equal of m for every natural number n. And finally, we say that the sequence is simply bounded, and we just say B, if, let me move this a little bit upward, if it is both upper bounded and lower bounded. We can give an alternative definition of a bounded sequence as follows. There exists at least one m real such that an in absolute value is less than or equal to m for every natural number n, or alternatively there exists at least one a real number and at least one b real number such that an will be always between a and b for every natural number n. We are now in a good position to state the theorem on monotonic sequence. There are two versions of this theorem. We'll first state the increasing version. Let an be a weakly increasing sequence. There are two possible behaviors. An tends to plus infinity, diverges to plus infinity. Second possibility is that an converges to a real limit r. And in both cases, the limit of an for n that goes to infinity is equal to the supremum of an for all possible n. Okay, so what we are saying is that if we have a sequence which is weakly increasing, we can only have these two possibilities. We can visualize this Basically, this first idea is just like having a sequence that clearly will diverge to plus infinity, and of course there is a possibility that this is a weakly decreasing sequence. The other possibility is that the sequence will converge to some limit L. And we are now going to prove this. Proof. Now, of course, we'll start with the first possibility, namely the fact that an will diverge to plus infinity. So, in this case, we know that the supremum of an for n into the natural numbers should be equal to plus infinity. So let's see if we have this, if we have that the supremum of n is equal to plus infinity, it will suffice to prove that an will then diverge to plus infinity. So let's take m a real number. Then we know that since the supremum of an is equal to plus infinity, well, this implies that there exists at least one n0 into the natural numbers, such that an0 will be larger than or equal to m. This is just the definition of supremum. But because now, since an is weakly increasing, then this implies that an will be larger than or equal an0, which is in turn larger than or equal to m, and this must be true for every n larger than or equal to n0. This must be true, so that implies that an will diverge to plus infinity. This is nothing else than the definition of a divergent sequence to plus infinity. So let's summarize what we just said. We wanted to prove that for a sequence which is weakly increasing, we can have the possibility that the sequence diverges to plus infinity if the supremum of the sequence itself is equal to plus infinity. And in fact, we said, okay, let's start by assuming that the supremum is plus infinity, and we have just proved that indeed the sequence is divergent to plus infinity. Second possibility is the following. Let's now assume that the supremum of an is equal to a real number L. Then we would like to prove that an will converge to L. Okay, but basically this is just like proving that an will be definitively between L minus epsilon and L plus epsilon. Okay, so this must be true definitively, okay, for every epsilon larger than 0. So we would like to prove this. Okay, so let's give the proof now. So the proof is the following. We can say, okay, let's start by assuming that the supremum of an for n into the natural numbers is equal to L, well then certainly we know that AN will be always less than or equal L, which is in turn less than L plus epsilon for every epsilon larger than 0. Right, so this is always true. So basically we can also say that AN will be less than L plus epsilon for every epsilon larger than 0. This is just another way of saying the same thing. But not only this, we also know that there exists at least one n0 into the natural numbers such that an0 will be larger than or equal L minus epsilon, which implies that since the sequence is weakly increasing, an will be larger than or equal to an0, which is now, we know, is larger than or equal L minus epsilon for every n larger than or equal to n0. And this in turn proves the fact that an will tend to L. So this is to say that in the first part we have just proved, okay, we have proved this, which we could also rewrite just as this. So we basically have proved the right part of the inequality, okay, in the first part. And by then using the fact that the sequence is weakly increasing, we also proved the second part of the inequality. Okay, this is the second part of the inequality, and we have just proved this. So finally, we proved the entire theorem. We can make an observation now. So what we can say is that it is not necessarily a n convergent to L minus, as it is possible that an can become L in a definitive way. So what we are saying that we cannot say that the sequence is convergent to the limit L from the left to L minus, okay, because this would exclude the fact that an will become steadily equal to L. But this is indeed possible, so we cannot say that an tends to L minus. And okay, so this turns out to be only possible. This would be true if an is strictly increasing. An interesting corollary to this is the following. If an is two things, weakly increasing and also upper bounded, then it follows clearly that the only possibility would be that an will tend to L, a real limit L. Okay, but this is clearly just an easy to prove corollary. Let's pass now to the other possible statement of the theorem on monotonic sequence. So let's say we have another version of the theorem on monotonic sequences, and this will be the decreasing version, and again let a n be this time a weakly decreasing sequence. There are only two possible behaviors. First, the an diverges to minus infinity, or an is convergent to a real limit L. And in both cases, we still have that in both cases, we can say that the limit of an as n tends to infinity is just equal once again to the supremum of an for all natural numbers n. Okay? Now the proof of this is exactly the same as the previous one, but we have another interesting corollary of this theorem, the fact that if an is two things, weakly decreasing and the second as that is lower bounded, then these two things implies that the only possibility would be that an will tend to a real limit r. Okay, now that we have this theorem on monotonic sequence, we can apply this to introduce one of the most important constants in mathematical analysis, namely the so-called Euler's number, which is usually indicated with E. Now, to this aim, consider the sequence en equal to 1 plus 1 over n, all raised to the n. In relation to this sequence, we can state the following theorem. The sequence en satisfies the following inequality. En is always in between 2 and 3. This is true for every n larger than or equal to 1. Clearly, this is the sequence is just defined for n larger than or equal to 1. And the second property is that en is weakly increasing. And of course, if we prove both these two properties, then as a consequence of the theorem on monotonic sequence, we know that en will be convergent to some number, which will be something between 2 and 3, which is exactly the Euler's number. So, therefore, en tends, or better, is convergent to some limit L in the interval 2, 3, and this limit is the Euler's number E, which is 2.7, 18, 28, 18, 28, and so on and so forth. Let's start now the proof of this theorem. And we'll split the proof in many steps. The first thing we want to prove is that En is always larger than or equal to 2. Okay? Now, to prove this, we will be using the Bernoulli inequality. And just as a reminder, the Bernoulli's equality says that 1 plus x raised to the n is larger than or equal to 1 plus nx, and this must be true for every x larger than minus 1, okay, and for every natural number n. If we apply these for x equal to 1 over n, we get that 1 plus 1 over n, all raised to the n, is larger than or equal 1 plus n times 1 over n, which is exactly equal to 2. So this is just the proof of the first statement. Okay, so then let's go to the second part, which is the fact that En is weakly decreasing. Let's prove this part, which is to say, we can write this in green. We want to prove that En is larger than or equal En minus 1. So this is another way of saying that the sequence is weakly decreasing. Now let me start exactly from the thesis. Okay, so let me start exactly from the fact that En is larger than or equal to En minus 1, and let's elaborate on this. Okay, and we will find as a consequence of the thesis a fact that it is clearly true. Okay, so that will prove the fact that the sequence is weakly decreasing. Okay, so this is just like saying if we just replace En with the 1 plus 1 over n all raised to the n. Well, this is larger than or equal 1 plus 1 over n minus 1 all raised to the n minus 1. Okay? But again, this is true if and only if we just transform the first parenthesis with a common denominator, what we get is n plus 1 divided by n all raised to the n. This must be larger than or equal of, we'll have simply n divided by n minus 1, all raised to the n minus 1, but we can, instead of writing this parenthesis to the n minus 1, we will split this into a product. Okay, we will write that this is n times n divided by n minus 1 to the n times n minus 1 divided by n. And now we can do something. We can say that this is true if and only if we just bring this element to the left hand side, because we have two powers with the same exponent, we can just rewrite this as n plus 1 over n all raised to the n times n minus 1 divided by n all raised to the n larger than or equal to n minus 1 divided by n. And this is true if and only if if we multiply both terms on the left hand side, we have n squared minus 1 divided by n squared, all this to the n larger than or equal, n minus 1 divided by n. We can just remove the parentheses on the right hand side. But this in turn is just 1 minus 1 over n squared, all to the n, larger than or equal 1 minus 1 over n. But this is exactly the last inequality is the Bernoulli's inequality with x equal to what? Well, with x equal 1 over n squared with x equal to minus 1 over n squared, okay? And we need to verify that this x is indeed larger than minus 1. But this is just like saying that minus 1 over n squared is larger than minus 1. And if we multiply this by minus n squared, we get that 1 is less than n squared, which of course is true for every n larger than or equal to 2. Okay, so we can definitely say that this finally proves that En is larger than or equal of 2. Let's now prove the third part, namely the fact that En is less than or equal to 3 for every natural number n. To prove this inequality, we will resort to the, so this is the basic idea. Let's use the Newton's binomial formula, which I assume you to be familiar with. And if we want to express the power of the binomial 1 plus x to the n, we know that we can write this as 1 plus n choose 1 x plus n choose 2 x squared plus n choose 3 x to the cube plus n choose n x to the n. And with x equal 1 to n, we get the following: 1 plus 1 over n raised to the n, which is of course just En. Well, this is equal to 1 plus n choose 1 of 1 over n plus n choose 2 1 over n squared plus n choose 3 1 over n to the cube plus dot 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 n choose n 1 over n to the n. Okay, now let's develop the binomial coefficient. We have 1 plus, we know that this is basically 1, right? So because this is n divided by n, so this is just And if we develop the binomial coefficient, we get 1 plus, this is just 1 plus n times n minus 1 divided by 2 factorial times 1 over n squared plus n times n minus 1 n minus 2 divided by 3 factorial 1 over n to the cube plus dot dot dot. Okay, now notice that if we identify this part in each term, we realize that this part is less than or equal to 1 because this is a fraction that contains at the numerator n times n minus 1, whereas the denominator is n times n, so clearly this is less than or equal to 1. The same way, this part of the fourth term is again less than or equal to 1 because it will contain at the numerator n times n minus 1, n minus 2, whereas at the denominator we have n times n. So the same way we can identify similar terms in all the entire right hand side. So we can write that this is less than or equal 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, and of course this will continue up to 1 over n factorial. So now let's focus on this part of the right hand side, and we can say that this part is less than 1 plus 1 over 2. We are just replacing 2 factorial with 2 to the 1 and replacing 1 over 3 factorial with 1 divided by 2 to the second plus dot 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 1 divided by 2 to the n minus 1. So what we are saying here is basically, and we will prove this later, we are saying that 1 over k factorial is larger than or equal, is less than or equal of 1 divided by 2 to the n minus 1. We will prove this later, but let's assume the result for the time being. So we can then write that this part is just equal to what? 1 and 1. Of course this is just okay, let's rewrite this as 1, and then we have this sum. Let me say that if we focus on this, we realize that this is just a geometric series. Okay, we have a sum of numbers obtained by multiplying by 1 over half. So we can easily prove that this is less than or equal to 2. So finally we can conclude saying that this is just equal to 1 plus 2 equal to 3, which finally proves what we were looking for, so namely the fact that En is less than or equal to 3. Okay, so let's now see what are the key properties, okay, the key properties that we have used to prove this inequality. So the first thing is that n choose k, the binomial coefficient, times 1 over n to the k is less than or equal 1 over k factorial. Okay, how can we prove this? Well, we know that n over k is n times n minus 1, n minus k plus 1, all this divided by k factorial. What we have done here is isolating, then of course we need also to multiply by n to the k at the denominator. We then isolate this term, saying that this is less than or equal to 1, and therefore we conclude by saying that this is less than or equal 1 over k factorial. So this proves the first property. Second property is that 1 over k factorial is less than or equal 1 divided by 2 to the k minus 1, okay, which was this property. Okay, this is clearly k minus 1. Okay, so let's prove this property then. Since both sides are positive, this is just like saying that k factorial is larger than or equal 2 to the k minus 1. But this can be easily proved by induction. So let's do this. We have the base case, and the base case is that for k equal 1, we have 1 factorial larger than or equal 2 to the 1 minus 1, which is just like saying that 1 is larger than or equal 2 to the 0, which is 1, and this is easily proved. Okay, so base case is done. Then let's prove the induction step. And the induction step is the following. If k factorial is larger than or equal 2 to the k minus 1, then it follows that k plus 1 factorial is larger than or equal 2 to the k plus 1 minus 1, which is just 2 to the k. Okay, so starting from k factorial larger than or equal to 2 to the k minus 1, if we multiply by k plus 1 both sides, and we can do this because k plus 1 is a positive number, then, well, this implies that on the left hand side we have k plus 1 factorial. On the right hand side we can say that this is larger than or equal to the k minus 1. Well, instead of having k plus 1, we can just replace this with 2. And why is that? Because in fact, let me use a different color, because we say that k plus 1 is larger than or equal to 2. In fact, k takes value more than 1, so k plus 1 is larger than or equal to 2. Therefore, we can just replace to the right hand side 2. But this is nothing else than k plus 1 factorial larger than or equal 2 to the k, which is exactly what we were looking for. Third property that we have used is the fact that 1 plus 1/2 plus 1 over 2 to the square plus 1 over 2 to the n minus 1 is less than or equal to 2. Okay, we want to prove this. And in order to prove this, let's say that this number, which is just the sum of 1 plus 1/2 plus 1 over 2 to the square plus 1 over 2 to the n minus 1, we call this number s. And then if we multiply this by 1/2 on both sides, what we have is that 1/2 s is equal to 1/2 plus 1 over 2 to the square plus dot dot dot. The last term is going to be 1 divided by 2 to the n. And if we now subtract term by term, we have that s minus 1/2 s is equal, as you see, these terms will cancel one with each other by leaving on the right hand side 1 minus 1 divided by 2 to the n. But this is just like saying that, as you see, the left hand side is just 1/2 s equal to 1 minus 1 divided by 2 to the n, which implies, by just multiplying by 2, that s is equal to 2 minus 1 divided by 2 to the n minus 1. And of course this is less than or equal to 2, because 1 over 2 to the n minus 1 is a positive number. So this finally proves the third inequality. Okay, now let's conclude by now let's use all these ideas for the proof as follows. We have that En equal to 1 plus 1 over n raised to the n. This is, of course, this can be expressed by using the Newton's binomial formula as the sum k goes from 0 to n of n, choose k, of 1 over nk. And isolating the first term for k equal 1, we have 1 plus the sum k goes from 1 to n of n, choose k, 1 over n to the k. And now by using the property number 1, we can write that En is less than or equal 1 plus the sum k goes from 1 to n of 1 over k factorial, just replacing, just using the property 1. But this, now using the property 2, we know that if we replace 1 over k factorial with 1 over 2 to the k minus 1, we get a higher number. So we can write this as 1. So let me say that in this case, we're just using property 1. In this case, we're just using property 2. So we can write now 1 plus sum k goes from 1 to n of 1 over 2 to the k minus 1. And now, using the property 3, remember that the property 3 is saying that the sum to the left, this sum to the left is less than or equal to 2. So this implies for us that this is less than or equal 1 plus, we just proved that the sum of for k that goes from 1 to n of 1 over 2 to the k minus 1 is just equal to 2 minus 1 over 2 to the n minus 1, which of course is something which is less than or equal to 3. Okay? And this concludes the proof. Now let's make a final observation. If An is weakly decreasing and an, for example, is less than 14, okay, so we know that each and every element is less than 14 for every natural number, then we can certainly say that an is convergent, okay, because this is clearly one of the cases of the theorem on monotonic sequences to a real number L, and we know that L is going to be less than or equal to 14, but it would be totally wrong to say that L is less than 14. This would be a total mistake. And so just as an example of this, let's see what happens if we have an equal to 14 minus 1 over n. Certainly we can say that an is less than 14. Each element is less than 14. However, we see that an will tend to 14. So we cannot say that L is less than 14. Okay, so, and this is valid in general, and it is worth pointing out this, saying that strict inequalities do not pass to the limit. This is something to keep in mind for the future.